So next I want to show you some more advanced type stuff that we would have done in class if we were regular classes, but we're trying to do remote learning here, so we'll do the best we can. Usually this would take about an hour, but I'm going to see if I can get it crushed down to about 15 minutes and show you some of the more advanced stuff that you can take in university and some of the stuff that you guys have learned actually leads into. And the first thing we're going to do is we're going to expand duality a little bit. So then you guys have taken some basic idea behind duality, the whole particle and wave nature of light, and I showed you how it actually applies to electrons and pretty much everything. But we're going to expand on that a little bit. Okay, so first of all, the basics type stuff. If you have momentum, you have to be moving, and motion is a wave property. So therefore, momentum is more of a wave measurement than a particle measurement. So on the other hand, if you have position, you're not moving, therefore you are not a wave, you are acting like a particle. So moving and momentum is a wave type thing, location and not moving is a particle type thing. You can't do both simultaneously, therefore you can't measure both at the same time. You can't be moving and not moving at the same time, so you can't measure both at the same time. So if something's just sitting there, it's not really that its momentum is zero. The momentum doesn't really apply to it because it only applies to things that are actually moving. So if you decide to measure one or the other, you can actually destroy part of an object's nature, limiting its options for existence. And we'll get into sort of what that means a little bit later. So, for example, if you decide to observe an electron or anything else, you will then cause it to act like a particle, because if you observe it, you know where it is, you're giving it location. If you give something a location at any time, it's a particle thing, not a wave thing. Therefore, it can't act like a wave, it has to act like a particle. Okay, I know this is getting kind of fast, kind of weird, but this is the basic ideas. All right, so there's two really important stories that you've probably heard of, especially if you have watched Big Bang Theory. One is the Heisenberg uncertainty principle. So suppose you got a photon, light photon, bouncing around inside of a box. It's all like mirrors inside, just bouncing around. And what you do is you put a divider, like a double-sided mirror, right down the middle of the box and sort of cut the box in half. Which side is the photon? Is it on the left side? Is it on the right side? Well, since location is a particle property and you can't actually see it because everything is sealed, it is acting like a wave because you're not seeing it. Therefore, it exists everywhere simultaneously, and you can't really answer the question of where it is because it doesn't really have location because you're not seeing it. So it can't act like something that has location. If you'd actually open the box and can magically see it and say, hey, it's on the left side or right side, then you could actually give it location. Until then, really, the answer of location doesn't really apply to it. Another common way of Schrodinger's cat, which again you've heard of if you've probably watched Big Bang Theory. There's a couple of variations of the story, but whatever. You get a cat and a bottle of hydrocyanic acid or in a sealed box, something like that. And the classic story has like an atomic clock attached to a hammer or something like that. Anyway, so the basic idea is there's two possible options. Either the cat is fine inside the box, or the cat is not fine because the Geiger counter radioactive hammer has broken it and it's not fine. Since we can't know which one it is, it's not either, it's actually both simultaneously. The cat is sort of both alive and dead at the same time, because since we can't actually observe it and limit its possible existence to one or the other, it can be considered both simultaneously. I know this sounds really stupid, but that's the basic idea. So until you actually look and limit its existence to one option, we can't know for sure, and sort of both at the same time. All right, so what's the point? Well, the point is if and how we choose to observe or interact with something actually determines how it can actually behave. Duality is not really about being both. It's also about how options of your existence are actually limited by how you are being observed. So let's go back to the Young experiment that you guys have done, where particles or light goes through two openings, makes an interference pattern, and I showed you how this is does a lot of other cool things, whatever it is. But that basic Young experiment, took it in grade 11, we reviewed it in grade 12, basic Young experiment. So waves go through two openings, make the interference pattern, get the maximums. You guys have reviewed this already. Now, when the exact same experiment is done with single photons, you still get a pattern, which makes no sense because it's an interference pattern. Minimum, you need two things to interfere. Well, you're only sending one photon at a time. It should go through one hole or the other hole and hit the back and, the detection screen, and that's it. But it doesn't. It'll actually make an interference pattern when you're only sending one at a time, which doesn't make any sense. So how is it possible if there's not a second wave source to interact with? Like it's really, really strange. Well, let's go back to those electrons we were talking about. The same experiment has been done to show the duality of electrons beyond their ability to refract through crystals. So I showed you guys way back when that they showed that electrons in anything actually travels as a wave because they did Snell's law with electrons in crystal. Well, you can do the Young experiment with electrons and they will also make an interference pattern. So with two electron sources, you will get the exact same interference pattern that light does, which once again shows everything travels as waves. And just like photons, you will create the exact same pattern when single electrons. Again, this doesn't make any sense. You're sending single electrons through the openings, and they will still make an interference pattern. But again, how is that possible when you're only sending one at a time? That doesn't make any sense. But what's also really cool is when detectors are set up to determine which slit emitted the electron, the pattern will actually disappear and you get two blobs of electrons. So what they'll do is they'll send detectors so they know which way the electron, did the electron go through the left hole or the right hole? But when you set up those detectors, you know the electron's position at some point, you know where it was, then it acts like a particle, not a wave, and it goes straight through like a bullet would and hits the screen. You get two blobs. So instead of an interference pattern, you only get two blobs of electrons, one for each hole. Really, really, really strange. So let's go back to duality. Once you try and find an electron's position, it loses its wave properties and acts like a particle. That's why you get two blobs. When the detector is turned off, the pattern will reappear. So it's really, you go back and forth, it's really strange. This even occurs when the detector is turned on when the electron's in mid-flight before or after the slit. So what this is really, really, really strange is even if you put on the detector after the electrons have gone through the two slits in the Young experiment, if you turn the detector on at any point, the electrons will act like a particle and will have gone straight and make two blobs. It doesn't matter when you put on the detector, you put on a detector, you get two blobs instead of interference pattern. So what? Well, first things first, everything is a form of duality. That's just the way it is. There's no way to get around it. And I remember being in university learning this stuff, and some people had a hard time accepting this type of stuff because it was so strange. You can either interact with stuff as either a particle or a wave, especially if you're a cat. And that's the good old Schrodinger's cat type of joke. And if you're into physics and Schrodinger's cat type stuff, this cartoon is hilarious. Now, the other part that kicks in is Young experiment has some major possible consequences. Not just a cool light experiment that I showed you guys in grade 11 where light cancels off light. There's some other stuff when you connect the duality to it. Consequence number one, light and particles seem to respond and act like waves or particles depending if we choose to detect them at some point in time. And what's cool is they seem to have some kind of precognition, which they use at emission to determine how they act. For example, when those electrons go through the openings, there's no detector. There's no detector at all. And they go through the openings, and suppose they're going to act like a wave, and they bank way to the right because they're going to hit a maximum way towards the right. But then you turn on a detector, and all of a sudden it doesn't hit far to the right. It hits right in the middle, lining up with one of the holes because it went straight like a particle. Well, how did that light or electron, whatever you're using, know that you were going to put on a detector so it could instantly transport itself back to the middle? Well, that doesn't make any sense. It must have somehow known, sort of, kind of weird, that you were going to use a detector at some point, so it's going to go straight the entire time, not bank to the right or the left like a wave, and then transport itself back to the middle because you turned on a detector. That doesn't make any sense. So it's kind of weird. Now, if you think this is a load of poopy pants, they've done the experiment with photons released from stars billions of years ago, because they're billions of light years away, and they will only make a pattern if there's no detectors. It's really, really, really strange. Consequence number two, how can you have single things going through the Young experiment and still get a pattern if there's nothing else to interfere with? Well, maybe there is something there. A second object is required to come from the other opening to create any interference, but we cannot detect it. Even photons and particles we can detect seem to have connections to each other, when this is what you may have heard of called entanglement. Why are we unable to detect this other ghost particle, this other particle that's creating interference? Well, perhaps that's because it's beyond our measurements of our reality. What we actually live in is our reality, what we can actually feel and measure and interact with. And maybe it is beyond our measurements of reality. And then by definition, it could possibly exist in a parallel universe or dimension. So the Young experiment and having interference patterns when you're only releasing one thing at a time is actual possible evidence that there are parallel universes and parallel dimensions out there, and somehow the particles are able to connect and link to each other between dimensions. And it's kind of weird and strange, but that is one of the main ideas behind it. So if there are ghost particles in parallel dimensions for the particles and photons used in these experiments, well, there should be for yours as well. There's no real difference, which means if there's parallel universe dimension particles for those, there should be parallel universe dimensions for your particles. So there could be another you in a parallel universe dimension, just because of this whole ghost particle idea. Like, there's something really interesting going on. And this is one of the explanations for possibly paranormal activity, as well as a really common thing, which is deja vu. And, if you've ever had real deja vu and you go, wow, I can't believe this experience, whatever's going on right now, I can't believe it seems so familiar. I swear I've done this before. I've seen this before. It's really, really strange. Well, maybe you have in a parallel dimension, and somehow information is being connected from that dimension you and those particles to yours, and somehow information is being transferred between them. So it's really strange. And there's other different things that are possibly explained by this, but there's definitely something very, very strange going on. Things are definitely more complicated than what most people realize. And even modern experiments, there's one done in 2019, have shown very strange connections between photons, which were theorized by Einstein to have things called entanglement. And lots of people have theorized and worked on this. Basically, they took a light beam, they split it, and what they did is one of the beams, after they split it, they phase shifted it. So basically, they angled it differently, or they shifted what it should do. So it's just sort of like a change in direction type thing. But when they changed the direction to one beam, it had an effect on the other beam. So there's somehow some crazy connection between the two sets of beams, even though they only affected one. It's really, really, really weird. It's sort of like you have like twins. Maybe you got twins, and they're not together. One's at a park somewhere, and one's at home. And the one's at the park is playing football or something like that. And all of a sudden somebody shoves over the one twin at the park playing football, and all of a sudden the other twin at home all of a sudden falls over on their own. And that's sort of literally exactly what's going on here at this level. It's really strange. So it definitely shows there's some kind of connections that we really don't understand that are working on. It's really, really cool. Some kind of connection between particles and photons, and there's just a whole lot more going on. And this is what duality really leads into, some really, really mind-boggling stuff. So I hope this gives a little more background into the duality stuff that we talked about a little bit. And again, if we were in my regular class, we would have spent a lot more time on this and expand on this type of stuff, but this is a remote learning type version, so hopefully it gives you a little more appreciation. And go on YouTube, there's some great, fantastic videos that explain the whole duality stuff in more detail and the effects and the experiment stuff that I recommend if you like this. It's really neat to go look some more stuff like that up.